Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this essay is an introduction to neural networks. It's part of the course Analytic Methods for Lawyers, although I will say that I think this lecture is particularly applicable to a wide variety of people interested in machine learning, or really in just what are these things called neural networks. And at some level, neural networks are just composed functions. We've talked about composed functions before. You take a function of something, then you take another function of the result, then you take another function of that result, then you take another function of that result, etc. So they're a little bit like Legos. There are a certain number of pieces, they're called layers, not blocks, and you put them together to do something useful. And the reason they're so popular is actually kind of like why Legos are popular. There's enough variation in the pieces that with some cleverness, you can build what you want. You can be your own architect. And so they can be used for all forms of supervised learning, prediction, classification, something we haven't discussed yet, but which is going to be crucial when we study computational linguistics, which is sequence-to-sequence models. They can also be used for unsupervised learning tasks, like clustering or compression. And they can be used for many other forms of artificial intelligence, including generative models. Now, that generate synthetic faces, for example. You may have seen examples of that. And unlike most other machine learning techniques, not only is the whole network useful, but often you can make great use of pieces of them. You can recycle them. You can take, say, I'd like 70% of this network, and we'll glom it on to another network. So, and indeed, actually, sometimes, as we'll see, you train the network not really for the end result, but to actually get a good subcomponent. And no one, to my knowledge, says that you can do the same kind of thing with gradient-boosted trees or random forests or nearest neighbor methods. So that's one of the reasons they're useful. Finally, one of the reasons that they're so popular is that they happen to run very well on modern computer architecture, particularly those which have advanced graphical processing units. It turns out that the same thing that makes Grand Theft Auto look realistic, those GPUs, actually also helps neural networks. And so while neural networks have not yet completely displaced other methods of machine learning, and they probably won't do so in the near future, and maybe there'll be something better in the years to come, right now they are the dominant contemporary method in the field. So the purpose of this essay is to give you a basic understanding of what they are. Later I'm going to look at prediction, classification, compression, sequence-to-sequence models, how exactly the magic works, and a bunch of other stuff. But for right now, let's start with the basics. As with painting and many other things, a lot of this is all in the prep. So let me prep you with a couple of notes. The first thing is for students in Analytic Methods for Lawyers, which is to know that there are some videos and some essays that are more important than others. This one is right at the top of the list. You've got to read the associated notebook and maybe watch this video several times. If you don't have questions, please let me know, because without an understanding of these basics, the rest of the course, which is going to focus pretty heavily on neural networks, is going to be an exercise in misery. Second thing to know is every respectable computer language these days has an implementation of neural networks. So Python users, for example, can use TensorFlow and PyTorch. Julia users have Flux and Mocha. They have indirect access to TensorFlow. C++ users, again, TensorFlow, Caffe, Microsoft Cognitive Toolkits. R users can use MXNet and others. And it gets more complicated than that. And if you are in the field, you're going to hear these terms bandied about, because there are things like Keras, which is sort of a high-level interface to TensorFlow. So those are some of the frameworks. The other thing you ought to be aware of is that although each of these frameworks has very similar functionality, they're going to differ in their details and their nomenclature. So for example, what's called a dense layer in TensorFlow is called a linear layer in Wolfram language. And different frameworks break up these layers into different parts. So for example, an activation function might be bundled right into a dense layer in many languages, but in Wolfram language, it's a separate layer, which is the correct choice in my opinion. But if you learn one framework, it's kind of like Latin, or at least so they say, since I don't really speak Latin, but it will definitely help you understand the grammar and the concepts of the remainder. As of version 12.2, Wolfram language has bet on MXNet as its low-level implementation, but it provides a nice, rich, Wolfram-y interface to MXNet. And yes, there are ways of accessing the very popular TensorFlow by going through Python within Wolfram language, but that's a little more advanced than I want to cover in this course. Third prep note, we need a little bit of math theory here. So what we're going to be studying is what are called feed-forward neural networks. There are other kinds, but we're studying feed-forward ones. And one of the reasons that feed-forward neural networks, even with the simple layers we're going to study here, is that they are what are called universal function approximators. There's a Wikipedia entry and actually a good website here that explain this in more depth, but the idea is that even with a neural network with very few layers, taken from a small set of possible layers, can make predictions that are as close as you want to the target data. Another way of articulating this is that neural networks can have essentially zero bias. Now, that doesn't mean those networks will generalize well. They might, but if you reduce that bias a lot, the odds are that you're going to end up chasing noise. You're going to be guilty of massive overfitting. But if you just want to fit the training data, a large enough neural network will get you as close as you want. With that, let's turn to layers. Neural networks are composed of layers, and really a layer is just sort of a function. It has a little more in it, but at bottom it's a function. Now, some of these functions have parameters that can change during the training of the network. So for example, imagine, and in some sense therefore they are function of functions. For example, imagine a function that's a function of some parameter p, and that in turn yields a function that is 3px, okay? So that if we change p, if p is 1, the function is 3x. If p is 2, the function is 6x. And so by changing the parameter, you change aspects of the function. Now, those parameters, there could just be a few of them, or there could be a lot. And there are also layers you should know that do not have any parameters. They're not trained. They just do what they do. And in fact, that's what we're going to start with. We're going to start with one of those layers that just does one thing. It's probably the simplest layer, and what it does, though, is it performs its computations in parallel. So if I give it 20 numbers, it will do the computation on all 20 numbers essentially at once. It's sort of like automatically mapping your function over a list of arguments. And the first argument to element, this is implemented in Wolfram language with element-wise layer. And element-wise layer takes an argument. That argument can be a function. And here's one. Here's just doubles whatever it sees. If it sees x, it returns 2x. And so I can assign that layer to a symbol, so I don't have to keep saying element-wise layer x goes to 2x. I can just say doubler. And when you execute this, you get a little object back, and it has some data, some details on what's inside the layer. And if I click on this plus thing, it's going to tell me that here's what it does. It takes a number and it multiplies it by 2. Here are its input ports. Here's what goes into the layer, into the Lego block, which is going to be an array of something. And what's going to come out is an array of something. Okay? So that's our friend doubler. If we want to get information on what's really going on with doubler, we can get its properties. If we don't know what its properties are, we can just ask one of the properties is properties itself. And so here are all the things we could learn about it, all sorts of fascinating things. Some of these we'll actually look at. Many of them, like topology hash, we will not. All right, but one of the things we do want to look at is the input port names. It's often useful to know the names of the hookups that go in to a layer. You can't change those in general. Those are fixed, so you better know what their names are. All right, and as it happens, there's only one hookup to doubler, and it goes by the name of input. And by the way, that is actually a string, not a symbol, which we can see right there. Okay. All right. So let's actually see what doubler does. And so the input to doubler, it can be something else, but sort of the canonical way to do it is to make it an association in which the keys correspond to the input ports of the layer. So we need one of the keys to be input, and here's our input, a list 2, 3, negative 2.4. And if I run doubler on that, it just doubles everything. Okay? Something you should know is that one of the great things about Wolfram language is you can just put a symbol in many cases. You know, this is a perfectly legitimate expression, right? I can say QQ of Z, and it doesn't say, hey, I can't do this because I don't know what QQ is, and I can't do this because I don't know what Z is. No, it'll just return something, okay? So that's a very useful feature, but does not work in the neural network framework. The neural network framework, generally speaking, it wants the inputs to be numbers. That's what neural networks work on. And so ultimately you've got to boil everything down to a number. You've got to boil a word down to a number. You've got to boil a picture down to a number, an audio file down to a number. And we're going to learn that there's something called net encoder, which is going to help you convert things that aren't really numbers or aren't numbers in the right way into numbers. But for now, if you try to give it symbolic input, as I do here, it's going to give you a failure message with, I think, a reasonably helpful explanation of what you've done wrong. Okay, so layers also produce outputs. In fact, sometimes they produce more than one output. And again, it would be useful to know the names of the connectors that are sticking out of the layer. So the way we get that is through this information output port names thing, and we learn, hey, there's only one connection coming out of a element-wise layer here, and it's output. Okay? I want to show you that there are other things you can stick inside an element-wise layer, and in fact there are named functions where you don't have to say exactly what the function does. For certain of reserved strings, it knows. And one of the most common of these string representations of functions is ReLU. What's a ReLU? ReLU will just generate the ramp function. What's the ramp function? The ramp function says if the input is less than 0, it just outputs 0. It doesn't matter if it's -7, -4, it's just going to return 0. If you give it something bigger than 0, it's just going to return what you gave it. And so it sort of zeroes out things that are less than 0. So here's how we create a ReLU layer. I'll call it ramp since that's what it does. And we can see how it operates by just running our data association here through it, and we'll just use the symbolic name ramp for the ReLU that we created. And you can see, okay, 2's positive, so it just keeps 2. 3's positive, so it just keeps 3. Oh, but negative 2.4 is negative, and so it will output 0. Well, that was a layer that didn't take parameters. Now let's look at one that does want parameters, the linear layer. And probably it's the layer that we will use most in this course. It has one argument and then some options. The first argument says how many numbers should come out of the layer. And the optional input let me say that again. The input option tells you how many numbers or what shape is the data going to be. So here it's saying I expect to see a length 3 vector, and I'm going to output a length 5 vector. So let's create our first linear layer. There it is. You'll notice it's going to tell you, hey, the input's of size 3 and the output is a vector of size 5. You'll also notice it has this badge of shame uninitialized here, meaning that although this layer does have weights, at present those weights, there's no value is assigned to those weights, and so you can't actually use this to perform an operation. It's just sort of a dormant static thing. And again, if we click here, we can get all sorts of information on the linear layer. It's going to tell us that internally it has 2 arrays, weights and biases, and that the weights are a matrix that's 5 by 3, and the biases are a vector that's size 5. It's telling us there's one input port and one output port. And if we ever didn't want to click on the button, we could simply say, hey, could you please give me the input port names and the output port names for this layer? Okay, so supposing also again I didn't click on that button, maybe I did this and I suppressed the output, so now I don't have a button to click on. So we can ask it for information on the arrays, and it will tell us, okay, there are 2 arrays, a list of biases, a list of weights, and at present their value is, quote, automatic, which really means that it doesn't know what the value is. It's just kind of waiting for you to tell it. And the way to activate a linear layer or other layers, or in fact lists or graphs of layers, is the command netinitialize. Netinitialize will take any of the learnable parameters in your network or layer and give them random values. And yes, there are fancy ways of controlling the randomity, but right now we're not going to go through those. So let's run it. And now you'll see that the badge of shame, of uninitialized shame, is gone. And so there's a picture of our network. Notice this is just sort of a symbolic representation showing 3 going to 2. It does not correspond to our actual network here. If we actually look at the arrays themselves, now that it's initialized, what we're going to see is that there's something called a numeric array. The reason that they're presented this way is that while in my little toy example we've got 5 by 3 matrices, in real world we might have 1,000 by 2,000, and really it's kind of a nuisance if it's going to print it out that way. Plus, this method of storage is more compact. If we want to see what the actual values are in form that humans can understand, remember, normal is what we often use to sort of take information in an object and make it more human readable. So we can just map normal over the arrays. And what we see is that at the moment the biases were all initialized to 0, and that the weights are indeed a 5, 1, 2, 3, 4, 5 by 3, 1, 2, 3 matrix. If we wanted to, we could assign the weights value of an array to a symbol. So I could say, hey, for future reference, I want to know what those weights were. And so that's all I'm doing here. And you can see that it's 5 by 3 because I'm just asking for the weights key into this array. And if I wanted to, by the way, I could not use net initialize to give values to the arrays. I could force my own values, values onto those arrays. So here I made up an array, here I made up a vector of numbers, and now I'm going to force the initialization by saying, hey, I want your weights to be my initial weights, and I want your biases to be my initial biases. So there you go. And it is in fact initialized. The badge of shame is gone. All right, so that's the architecture of a linear layer, but what does it do? All right, what it does is it takes the dot product of the weights with the inputs and adds the biases. So I'm going to show you this. Here what I'm going to do is I'm going to take the linear layer that I created with my own weights, and I am going to see, and I'm going to apply that, I'm going to apply that to a vector 2, 3, 5. The other way I'm going to do it is I'm going to take my initial weights right here, dot them with 2, 3, negative 5, and then add in my initial biases. So here I'm doing the computation in a neural network sort of way, and here I'm doing it more by hand. And we'll look to see what the expected output is, the actual output is, and whether our test shows the equivalence. And if you eyeball them, you can see that they're the same, and Mr. Wolfram thinks that they're the same too. So the point here is to show you exactly what it is that a linear layer is doing. Well, we can play Legos with just 2 Lego blocks. We're going to have an element-wise layer and a linear layer. The command that's going to ultimately assemble all the layers properly together is netgraph. But the way we're going to do it is we're first going to specify what blocks do we have. Second, we're going to say how do the blocks connect to each other, and then actually there are some third arguments for things that aren't really blocks. Okay, so how do we designate the blocks? We're going to have an association. The keys in the association are going to be names of the blocks, of the layers, and then the values of the association will be the layers themselves. And so here, my nodes are going to be a linear node, a doubler node, and our ramp node. Okay, so that's what we're playing with. There we go. Now we got to explain how we connect the nodes. And here we're going to talk about Netport. Here's the idea. The layer netports have inputs and outputs for right now. Yes, they could have other things, but for right now, all we have are inputs and outputs. And therefore, what we want is for the input hookup to have something coming into it. And the output connector should be sticking something out for something else to accept. Okay? So the idea is generally output goes to input. Now, one complexity. There are some ports that they're not layers. They're basically just sources of data or recipients of data. And so in my example, I'm going to have some input data, the stuff that I feed in to the network. And in fact, we saw that right here, right? Here's that input that I'm going to feed in. So the idea here is that my input goes into the input port of the linear node. The output from the linear node goes into the input port of the doubler node. And it goes into a receptacle of data called peek that will let me peek in to what is coming out of the linear node. The doubler node, the output from the doubler layer, goes to the input of the ramp layer. and the output of the ramp layer goes to another non-layer port, a receptacle of data that I will call output. Okay, so that's the language of Netport, and these are going to form the edges of our graph. All right, now we are basically ready to make our net graph. Here are the arguments. Here's net graph. The first argument is what Lego pieces are we playing with. The second argument is how are the Lego pieces connected to each other. And then the only thing we need to do is to tell our net graph what form the non-layer ports are going to be in. And here I'm saying, hey, expect input in the form of a length 3 vector and produce peaks in the form of a length 5 vector. And so that is our net graph. And we can see a little picture of the net graph right here. A few things to note. You'll notice that this is pink. It's pink because it's uninitialized, and it really probably should be initialized before we use it. You're going to see a concept of the doubler, element-wise layer, and actually of the ramp layer here. And you'll see that our output ports are peak and output, and our input ports are input. And that's exactly what's reflected down here. All right, so I could initialize the neural net either by wrapping it in net initialize, in which case the things would be random, or I could have nodes that I had initialized on my own. Like here, this is my version of what the linear layer should look like. So if I want to have initialization, I'll just execute this code. And now, in my net graph, the Lego pieces that I'm playing with will already have had their weights specified in a way that I set up all the way back. Where did I set linear W? Right there. Okay, and so now I can create a net graph that's been initialized exactly the way I want it. And you'll notice, by the way, that now we have nice pretty pictures, and if I click on it, no more pink. Supposing though, supposing I did this, and I didn't have anything to click on. Well, I can get information on a graph, and one of the nice properties I can get is called a full summary graphic that gives a lot of information about what does the network look like. And so we have this picture, okay? We can see that it starts with an input node, which has dimensions of 3. It goes through a linear layer, out of which comes a vector of length 5, which goes to the peak non-layer port, and it also goes to the doubler port, which carries through to the ramp port. We're still preserving dimensionality of 5, and out of the ramp comes an output. So let's see if we can actually run our neural network on data. And I'm going to give it 2, 3, negative 5. And before we tell the network to do it, let's see if we can trace this out. All right, so the first thing 2, 3, negative 5 is going to do is it's going to go into our linear W layer, and we know that when we put 2, 3, negative 5 in, we get this negative 10, negative 16 thing out. How do we know that? We know that because we computed it up here. And then, yeah, that's what's going to come out of peak, but it's going to go to doubler. Well, we know what doubler does. Doubler doubles things, so we should have negative 20, negative 26, ... 46. Then we're going to ramp stuff, and ramp is just going to set anything that's negative to 0. And so I predict we're going to end up with 0, 0, 10, 10, 46. Let's see if I am correct. And if we look at our output, it's 10, 10, 46, just as I hoped. And if I look at our peak, that's what's coming out of the linear layer, and that's exactly what we predicted too. So I think we should take a bow at this point. But Two additional things to notice. The first is that if I were to delete the peak port, there would only be one output port, right? And when there's only one output port, the default behavior is to just produce the output and not do it in this association form, just so you know. The second thing you'll notice is I gave it lots of data, 2, 3, and -5, and I didn't need to do map or anything like that. Neural networks love to map on their own. And so here, for example, you can see this very explicitly, where I'm going to take lots of data, and it's going to produce lots of length 5 outputs. We're getting to the fun stuff, but just be patient. You need to know we can perform surgery on networks, and one of the things we can do is delete parts of them. Here I'm going to delete the peak port, non-layer port. All right, now if we look at it now, there's no peak port, and in fact it's just a chain all the way to the end. And in fact, as I mentioned, if I take our new network and I run input through it, it's not going to produce an association, it's just going to produce an output vector. I could also delete a layer, and let's see what happens when I do that. When I do that, you'll notice, this is because I'm running it on the original network, not on the peak deleted network. I took out an intermediate node. Doubler used to be right here, and it was smart enough to figure out that, oh, you probably don't want a disconnected network. You want the linear to hook up to the ramp. We can also actually add layers to a network that exists. So here I'm going to take a new layer called last linear, and I'm going to use NetAppend to append this last layer to our network, and you'll see a picture of it. And so now we have a new layer. I didn't give it a name, actually, so it's just layer 4. And by the way, this is all layers in a chain, at least, will just have numbers. I could also refer to this as 1, 2, 3, and 4. But if I don't give it a name, then the only thing I can refer to it as is 4. Just like doctors can do diagnostic tests, we can too. I can say net extract. It's like a biopsy where I take something out, and here what I want to do is I want to go into the linear layer and get its weights. The command to do that is net extract. I get this numeric array object. I could normal that if I want the numbers, or I could just matrix plot it to get a feel for what it looks like, and you can see it's a 5 by 3 array. The prep work on the architecture is done. Now let's just get our data and train away. So we're going to slurp up the Boston Holmes data that we've seen many times in this course. And you remember what that looks like. Here's Boston training 1. It's a rule in which the features are mapped to a target. So if I want just the features, I'm just going to get part 1 of the data, which is a 338 by 13 matrix. If I want the targets, I'm just going to get part 2 of that data, which is a 338 length vector, and I can do exactly the same thing for the test data. Okay, one more layer, I guess. We need a loss layer. That is, we've got to figure out, it's all well and good for the network to calculate something, which it can do right now, but if we want to train it, we want to minimize something. We want a goal, and the goal is always to minimize something. And here what we're going to try and minimize is the mean squared loss layer. Or actually, we're going to try and minimize the mean squared loss by using a mean squared loss layer. The idea is that this is just like regression. We're trying to minimize the sum of the squared residuals. That's really the same thing as minimizing the mean of the squared residuals. And what are the residuals? Well, we need 2 values. We need a guess and we need reality. So let's look at what ports can go in to a mean squared loss layer. And there's input, that means the guess, and target, that means reality. So we are now ready to build BostonNet. Okay, here are the layers that we're going to use. First layer is a linear layer. It's going to output 50 numbers. It expects input of 13. Then we're going to run it through a ramp. Then we're going to run it through a layer named compressor, which is going to take 50 numbers and boil them down to one number. And also we're going to need a Lego block that I'm going to call MSE to compute the mean squared loss layer. Okay, so let's look at our edges. Here are our connections. We're going to start with something called features. That's the data that we're going to use for prediction. We're going to feed that into the input port of the linear layer. The input port of the output port of the linear layer goes to the input port of the ramp. The output port of the ramp goes to the input port of the compressor. The output port of the compressor goes to two things. It's going to go to the input port of the mean squared error layer, and we're going to peek at it. We want to know, hey, what are you actually predicting? Because that's what that one number is. That's the predicted price of the home. And then what else do we need to feed in to the mean squared error layer? It needs to know what the reality is. Where are we getting that from? We're going to get that from a non-layer port called targets. So that non-layer port is fed in to the targets hookup of the MSE mean squared error layer. And now we're ready to build. So, what are the arguments? Here are the Lego blocks. Here are the connectors. And now we just need to explain to the network what form the data is coming in at. It's going to see features. That's a length 13 vector. It's going to see targets. Those are scalars. That is, those scalars are just numbers not wrapped in any list or anything. What do we want to output? I want a scalar output. I don't want to know that the value of the home is list 31.2. I want to know that it's 31.2. I'm going to net initialize this while I'm at it, and I'll wrap the whole thing in information so I can get a picture. Okay, I forgot to evaluate something, so I've fixed that. And now we get a picture of our network, and we can see that we have features coming in. The length 13 vector goes into a linear layer, out pops a length 50 vector, which goes into a ramp, which zeroes out the negative values, goes into a compressor, which turns our length 50 vector into a length 1 vector. That length 1 vector is our output to the predictions non-layer port. It also goes into the mean squared error layer, which is also fed the targets, and now it can compute the difference, the squared error between the targets and the prediction, and it outputs that as the loss. So that's what we do, and now we can just make sure it's going to work right. So let's just take the first 5 features of our data and the first 5 targets, and let's run it through our untrained network. We haven't done any training yet. This is just sort of basically random initialization, but it does produce values, and thankfully it produces 5 values. Here are our predictions for the values of homes. I think these would be underpriced, but in any event, we could also see what's the sum of the squared residuals of the difference between the predictions and the targets, and you can see that's 81,664, which I believe, if I add those up, and I could learn to capitalize, we would get exactly the same number. Okay, at long last, we're ready to train. Here's the idea. We're going to feed batches of features and target into the network. The network is going to make a prediction and compute a loss. And then, through a magical process, which we're going to wait until several more lectures to describe, the training function is going to adjust those parameters of the layers that in fact have trainable parameters. Here, those layers are linear and compressor. We're then going to run another batch through the network. Or if we've finished all our batches, we'll start a new round and run through the first batch of data again. Again, we're going to magically adjust the training parameters. If you don't like the word magic, I will let you use the term backpropagation. And we're going to keep doing it over and over and over again until at some point the training stops. And we'll discuss how you stop the training, but for now, we'll just assume at some point it stops. We then will have a network that has the same architecture, layers and connectivity than it did before training began, but the parameters are different. And I suppose if you love Lego metaphors and could imagine such a thing, maybe the Lego changes colors while it's being trained. It's still the same boat that you made or train that you made, but now the colors are different. And what that means is that when the network gets an input, the output will be different than when we started the training process, and hopefully it will correspond to the target better. The command, the Wolfram language command for training is nettrain, and it's got a very straightforward argument structure. The first, it's kind of like classify or predict. The first argument is the neural net with which you're training. It doesn't have to be initialized. If it's not initialized, nettrain will initialize it for you. If it is initialized, it will leave it alone. The second argument is the data. There are lots of forms that data can be in. For right now, I want you to use the following. I want you to use an association in which the keys match the non-layer netports in the connectivity segment of the net graph and the outputs that you need. So here, the keys will be features and targets. And if we wanted to, we could also specify a type of prediction. There are also lots of optional arguments you can use. You could say, hey, I only want certain information out of the training process. Maybe I only want to know the number of rounds that the whole thing took. Or maybe I just want the trained network. I'm going to be greedy and ask for all the properties. That means I want to know everything you learned during the course of your optimization. Now, nettrain takes beyond this many options, which have sub-options. We're going to learn a few of those along the way, but to learn more, you're going to need to look at the Wolfram documentation or more advanced videos. We're going to now begin our training. First, we're going to put the data in the right form. Let's just show you what that looks like. So we've got features, lots and lots of length 13 features, and finally we have targets, which is a vector. All right, enough scrolling. Let's suppress that output, and we're ready. Okay, we're going to say nettrain. Here's our architecture. Here's our training data. I'm greedy. I want everything. I want to know everything. And I have here a snapshot of what training is going to look like when you run this, so that if you're viewing this as a static notebook, you can actually see it. But since we're in a video right now, let's actually run the training. Here we go. All right. And you can see the errors decreasing, the losses decreasing. That's good. We could learn that it's done 8,700 and some batches, except yes, I say that it's going on. It anticipates it's going to run 43,000 batches through 7,200 nodes. Here's how many examples it has trained so far. It's using something called Atom. We'll talk about that about 3 lectures down the road. We're training it on a CPU since Macs don't have GPUs that play well with MXNet, a point of some consternation. We'll learn about the learning rate about 3 videos down the road, and here is the lost, some of the squared errors that it's currently experiencing on the current batch, and here's what it was on the current round, and we're done. So we get out a nettrain results object that has a little picture of some of the things that it found. And so what you did see, right, we saw this, we saw a orange line that descended as we went through our rounds, and so the predictions got better and better. What can we get out of a nettrain results object? Well, to find that out, we're going to take the normal of it, and then that's an association, and we'll get the keys. And so here are all the things that you could learn about the training that you just did. For example, maybe I want to look at a picture of my training history. And you can see that most of the work got done by 4,000 rounds. After that, things settled down. And this, by the way, is very typical, where you get the biggest bang for the buck in the early rounds, and then things get marginally better thereafter. I could say, hey, why'd you stop training? And it'd say, well, implicitly, you had a default value for the max training rounds option, and that's what I bumped up against. There are other reasons that training might stop, which we will cover in either the next video or the one after that. In any event, though, probably what we want is the trained network, and the property to retrieve that is trained net, and we'll assign the results to Boston TN. And so it's a neural network. It has the same architecture as the one we started with, but now the weights are different. And in fact, we can see what happens. Let's take the first 5 inputs of our training data. Here's our training data. We start with that. Take the first 5 features and targets and apply our new neural net to that. And we're getting values. And those look much more like the values of home prices. So we did it. We just successfully trained a neural network. Before we go on, though, I want you to kind of understand what is going on so it appears a little bit less magical, and so you can understand what people are doing right and wrong if you are confronted, for example, in a litigation situation or otherwise where someone's trying to persuade you that their neural network is awesome. We're going to make use of matrix plot. I think we've seen matrix plot before, but it's just a picture of a matrix. So here you can see -7's kind of blue and 9 is kind of orange. So it's by default operating on a bluey orange scale. All right, let's look at the initial weights that we had when we started training. This is just of the untrained network. And so we're going to look at the weights of the linear layer and the compressor layer. And you can see that this was a 50 by 13 matrix, and here are our weights for the compressor layer, and that was just a 1 by 50 matrix. We could try to visualize the initial biases, but it's uninteresting because the biases are all zeros, so you get a very uninteresting picture. That produced an error for reasons that really need not concern you. I'm going to fix it. And you can see it's very uninteresting. Everything's 0. Now, let's see what happens to those weights during training. To do this, I'm going to use some fancy code that you do not need to understand. But what you should perhaps understand is that during training, the training process produces an association that has tons of information on how it's going. Everything from what batch number we're at, to what the current weights are, to what the current losses are, all sorts of things, and that we can access that information and basically have it print out during our training process. And I've written a custom function that's going to grab the weights from the linear and compressor layers and print them out, and I'm going to tell it to do that every ½ second, and I'm going to stick that in an option called training progress reporting. And this time I'm going to tell it, hey, only go 30 seconds. That'll be more than enough. And so what I want you to do is to watch what happens to our weights and the fit. Okay, so here we go. And you can see the weights changing in the linear layer. You can see the biases, if you look carefully, changing. And now basically things have stopped moving in a visible way. Basically things have stabilized at this point, so we don't see much in the way of changes. And we're basically done. Okay. I'm going to write another function that's going to let you basically see a comparison plot. What is the predicted value of our homes and what's the actual value? We've seen comparison plots before in our study of supervised learning, and so We're going to run net train. Again, the only thing that's different here is the report is going to be a comparison plot. The things I want to grab are what does our network currently look like and what round are we in. The other thing I need to tell it is, hey, if you're going to produce a plot, I need to know what the data is that you want me to plot. So I provide that. And we're going to look at this every 1/10 of a second. And I think this is pretty cool. Okay, here we go. And you can see very quickly that the points are beginning to line up. They would fall on this line if everything were perfect. And as the training proceeds, you can see that the points are moving towards the perfect prediction line. They're never going to quite get there. But by 50–60%, nothing's changing. Basically, the network has found as much as it's ever going to find. And we're done. So this is essentially what you saw, which is at the beginning we had points that were, somewhat far away, like here, although many of the points, even by 14% of training, had gotten to close to where they should be. And by the end, except for this one little guy here, the points are lining up pretty well along the perfect prediction line. So that's, I think, a good visualization of seeing training in action. But of course, let's get a sense as to how well we did. And just as there are the classifier measurements functions for classify and the predictor measurements function for predict, we have the net measurements function for neural networks. The argument structure is much the same. You have net measurements, and then this is your trained net in the same way that with classifier predict, classifier measurements or predictor measurements, you would have your classifier or predictor here. This is your data that you're testing it on, and then I'm going to list two properties here that I'd like to see information on. One is the fraction of the variance that's still unexplained, and one is the R². And these two, by the way, sum up to 1. So we can see that I really did quite well, 78%. That's good. Let me show you one more opportunity here, which is instead of using net measurements, you can actually treat your neural network as a predictor and get all the things you get with predictor measurements. The way you do that is you apply your trained net to the test data. That's going to produce an association in which predictions is one of the keys, and you're going to extract that key, so you now have your predictions here, and then you have your reality here, which is the test targets. And so if we do that, we get what we've gotten before. We get our R², which is fortunately identical to what we just computed. We get a comparison plot, which, except for the fact that they use circles and I use dots, looks, as far as I can see, exactly the same. So those are ways of measuring how well your neural network has performed. And of course, once you have a predictor measurements object, you can use all the features of predictor measurements objects. So if you want to get a residual plot or a total square, you can do that. I've been pretty rigorous in how I've defined my neural network architecture with all that Netport stuff. I do want to show you that there's a simpler way. And you may be thinking, well, why didn't you just start with the simpler way? And the answer is that what I find is that where you do have very simple problems, yes, this simple method will work. But the moment you try to do something more complicated, you really need to understand what this is a shorthand for. And so I fear if I present the shorthand first, it will be confusing. So if you like this method, that's great, and you can sort of watch the video in reverse. That was a joke. All right, but what we're going to do is, instead of listing out all the nodes and all the connections, where it's just a chain, where you go from one node, a linear layer, to another layer, the ramp layer, to another layer, another linear layer, you can just use very abbreviated syntax. You say it's a chain, net chain. 50 is interpreted to mean a linear layer of 50. Ramp is interpreted to mean an element-wise layer of a ramp. 1 is interpreted to mean a linear layer of 1. You don't need to tell it the connectivity. It just assumes 1 goes to 2 goes to 3. And you do need to tell it what form the input's going to go into. The machine assumes that it's going to go into this first linear layer here. You'll notice I haven't even told it where the target goes. That's because it assumes that I'm going to put the data in a certain format so that it's obvious where the target goes. And then I do want it to output a scalar. So I've now defined our simple net architecture. If you want to see it, we could do this. We could do information simple net, and hopefully you know that what I want is full summary graphic right now. And here's a picture. Its input has 13 values. It goes to the first linear layer, which produces 50 values, which goes to the ramp, which keeps the 50 values, which goes to this linear layer, which compresses it down to 1, which goes to the output. Just to verify that this works, I'm going to train it for about 2 seconds. Here's my architecture, simple net. I do have to put the data, as I mentioned, in this special form where all of the features go on the left-hand side of a rule and the targets go on the right-hand side of a rule. So you'll notice that I haven't specified what the loss, there's no mean squared error node that I've set forth, and that's because Wolfram is smart enough to think, oh, he's ending with a linear layer. That means he probably wants a mean squared error layer to calculate loss. So again, it's making some assumptions, but oftentimes those assumptions are correct. Let's just make sure it works, and it does. Okay. What if I need to get information out? I haven't named the layers, so I can't ask, for net extract of linear 1 or linear. So I think I mentioned that the nodes, the layers are numbered, 1, 2, 3. And so if I want the weights from that first linear layer, this is how I do it. I'm going to normal them when I'm done, and then I'll matrix plot them. So there's a picture of the weights in the first layer. You don't have to either have a full specification as I did before, or that very abbreviated specification as I did just now. You can have something in the middle. So here, I'm not going to use just 50. I'm going to say I want a linear layer of 50 and an element-wise layer of ramp and a linear layer. And again, I could specify the connectivity as just 1 goes to 2 goes to 3. None of this output port goes to this input port, and this input port goes to that output port. I'm sorry, output port goes to input port. It's much more simple. I can declare our net graph, and I'll just say the structure, the architecture of these intermediate nodes. Intermediate nodes. Here's our connectivity structure, and again, I'm going to use this very simplified description of the non-layer ports. Let's see if we can actually fabricate a net graph that way. We can. Basically looks the same as the other net graphs that we've seen. Will this actually work? Well, again, net train, I first specify what our architecture is. I then specify our data here because I've used a simplified method of describing the network. I'm going to want to use this simpler method of showing the data structure. So we have all the features, a rule going to all the targets, and again, I don't really care what the results are here. So we'll just let it run for 2 seconds and make sure that it works, and it does. So that's good. We just scratched the surface of neural networks. I showed you some basic architectures and how they are specified in the Wolfram language. I showed you how to get some information out of a net and also some surgical procedures to alter or probe them. Finally, we did some basic training, and I tried to show you through visualizations what's actually going on inside the network. You also saw at the end simplified syntaxes for describing a network. Let me just say there's a lot more to learn, and we will cover some of it in the next couple of lessons ahead, but you should understand that neural networks is a gigantic and exploding subject. I've really never seen a topic explode as much as this one has, but I hope that this essay gives you a sturdy foundation on which you can build a richer understanding of this fascinating field. You will notice that there's an appendix. I am not going to go through that appendix on this video. Let me just tell you what it's about very briefly. You'll notice that I don't ever put two linear layers together. Instead, I insert some sort of nonlinearity, and you might wonder why I do that. And the answer is that putting two consecutive linear layers together is mathematically the same as one slightly different linear layer. If you want to know why that's the case, then you're going to love this appendix. But otherwise, you can just take my word for it and know that really it's not a great idea to put two linear layers right next to each other. Okay, that's it. Hope you enjoyed. Thanks.